Today I'm going to be completing part D of homework 2 for process dynamics and controls. Getting started here, we're going to be expressing the heat diffusion equation from C1 as an algebraic equation. And we did this previously with explicit differencing, but this time we're going to use the Crank-Nicolson differencing, as we later on are going to figure out that allows us for wider values of R with greater stability. But getting started here, the only difference between the Crank-Nicolson differencing and the explicit differencing is we're going to add another term to the right-hand side of our equation. So if you recall, in explicit differencing, we had our t, j, n plus 1 minus t, j, n all over delta t is equal to alpha times t j minus 1 n minus 2 t j n plus t j plus 1 n all over delta x squared. Now what we're going to add to this to make it Crank-Nicolson difference is we're going to divide our alpha by 2. We're also going to add a term that goes t n plus 1 j minus 1 minus 2 t n plus 1 j plus t n plus 1 j plus 1. Again, all over delta x squared. So before we move on, we already know we're going to sub out our alpha for our R value, which in this case is going to equal alpha delta t delta 2 delta t over 2 delta x squared. So moving on from here, we're going to go ahead and write this out with our R. So we've got our t n plus 1 j minus t n j over delta t equals our R times our t n j minus 1 minus r 2 t n j plus rt n j plus 1. And now we're going to go ahead and add rt n plus 1 j minus 1 minus 2 t n plus 1 j plus t n plus 1 j plus 1 all times r. Now you see here, now that we've got this n plus 1, we've got a couple terms on either side that we can possibly cancel with. So let's go ahead. And there's no delta t here, that is accounted for in R. There are some terms here that we can cancel out. So let's go ahead and split these up. So what do we have here? We got t n plus 1 j add 2 r t n plus 1 j minus t n plus 1 j plus 1 times r minus t r times t n plus 1 j plus 1 is going to equal t n j minus t r times t n j minus 1 minus 2 plus minus 2 t n j times r plus t n j plus 1. And now that we've got our like terms on either side, let's see what we can cancel out here. So on our n plus 1 side, we can see that we've got our 2r plus 1. So if we pull this term out, you can get our t n plus 1j times 1 plus 2r minus r t n plus 1j plus 1 minus r t plus 1j minus 1. There we go. And we're going to have that equal t n j times 1 minus 2r plus r times t n j minus 1 plus r times t n j plus 1. And this right here is our expression our algebraic expression for heat diffusion using the Crank-Nicolson differencing method. So now moving on, we're going to do another von Neumann analysis to see, or to prove that this R is stable for values greater than 0.5 as compared to our explicit differencing before, where values above 0.5 would result in instability. So let's go ahead and move on to that. All right, now that we've got our expression for the heat diffusion equation as an algebraic equation via Crank-Nicolson differencing, we're going to go ahead and do a von Neumann stability analysis to determine that the R value can be greater than 0.5 here without destabilizing, as we saw with the explicit differencing. And to get started here, we're going to do our same analysis with this J plus 1, J minus 1 temperature as we did before. And we're going to say that T at either n or n plus 1 at J plus 1 is going to equal T at J times E to the K IK delta X. And we're also going to say that T at J minus 1 is going to equal Tj e to the negative IK delta X. And plugging that into this expression up here, what we're going to get something like this. We're going to get Tn plus 1 J times 1 plus 2R minus R times E to the I k delta x minus r times e to the I minus I k delta x. It's going to equal t j n times 1 minus 2r plus r times e to the I k delta x minus, or plus r times e to the minus I k delta x. And then if we divide these out, we'll get expression that Tn plus 1 j over T n j is going to equal, make sure I do my algebra all right here, one minus 2r plus r e to the I k delta x plus r e to the minus I k delta x all over 1 plus 2r minus r e I k to the delta x minus r e to the negative I k delta x. Now, if you recall the cosine equivalency we were talking about before, where our cosine of k delta x equals r e to the positive I k delta x plus r e to the negative I k delta x over 2. You can go ahead and plug that in to this to get t plus 1 at j over t n at j is going to equal, go ahead and divide this out. I believe we're going to get 1 minus 2r times 1 plus our cosine k delta x all over 1 plus 2r times our 1 minus cosine k delta x. Now, looking at this expression, we know that cosine can only take on values between -1 and 1. Taking that into account, we know that this expression here must always be positive. Because in the case of -1, we would get a value of 0. In the case of +1, we get a value of 1. Whereas down here, in the case of -1, we get a positive value of 2, versus in the case of +1, we get a value of 0. So taking that into account, this entire expression is going to take on end behavior like 1 minus x over 1 plus x. If we recall, the von Neumann stability says that the absolute value of this expression must be less than or equal to 1 for our R value to be stable. And if we look at this for any value, 1 minus x will always be, the absolute value of 1 minus x will always be smaller than the absolute value of 1 plus x, meaning that this is always true. This value will always be less than 1, meaning that the algebraic expression found via Crank-Nicholson differencing produces an R that is always stable when compared to the R produced by explicit differencing. So now that we've proven that, we're good to go ahead and simulate this via code in Python. So let's move on to that. Alrighty, now that we've found our algebraic expression via the Crank-Nicholson differencing, we can go ahead and apply that to a 50 centimeter aluminum bar with a thermal diffusivity of 1 e minus 4 meters squared per second. That's initially at 20 degrees Celsius, same as our previous problem, but this time we're going to raise the ends to 50 and 80 degrees Celsius. We're then going to discretize the bar into 1 centimeter sections and solve the equations from our first part of D1 using a time step of 0.1 seconds using scipy.linalg solve banded for 10,000 time steps. And we're going to plot those simulated results. So to get started there, we're going to put in our known values. So we know our alpha, our thermal diffusivity that we were talking about, and it is 1 e minus 4 meters squared per second. We also know our dx, it is 1 centimeter, so we're just going to put 0.01 meters. And we know our dt, which is 0.1 seconds, so we're going to put that in as 0.1 seconds. And then we can solve for our r. If you remember, it is our alpha times dt over 2 over dx squared. That should be all right, but just to make sure, I'm going to go ahead and print out our r. Fantastic. That is perfect. So now we can go ahead and move on. All right, now similar to what we were doing previously, I'm going to set our n equal to 50 since we're discretizing this bar into 50 different 1 centimeter sections. I'm also going to create an array for our bar initially fully at 20 degrees Celsius. So I'm going to say t equals mp dot full array size n, all with values of 20. All right, that should be all good. And going on from there, we're going to go ahead and set our endpoints. So we know that our T naught, our initial temperature is 50 degrees Celsius at the one end of the bar. And we know that our endpoint, our T negative 1, is going to be 80 degrees Celsius. Alrighty, now that we have those points in there. All right, so next we are going to go ahead and create our matrix based off of that equation we figured out up on the board for the Crank-Nicholson. And to do that, we're going to kind of create an initial matrix of all of our 1 plus 2r, an r minus 1, and then our array of temperatures. We're going to multiply those, but we're going to call that initial array AB. And to create that, we're going to say AB equals mp dot vstack. And then we're going to do first part of the mp dot full of n minus 2. And then we're going to do negative r. Fantastic. And we're going to do another array that's mp dot full n minus 2. And we're going to do 1 minus 2 times r. And our final one is going to create that kind of diagonal shapes. We're going to do an np dot full and -2, and then another minus r. Make sure I've got everything in here. Fantastic. Nope. All right, I realize I made a couple mistakes in here. I just need to change this to a plus. I forgot to put my entire series here and do another set of parentheses. Perfect. So that should be all good. All right, now we are all good to go ahead and start to make our plot. So to start this out, we're going to do, again, our distances. So we're going to say our IDX is going to equal np dot a range n. And then we got to make our figure. So we're going to say fig equals make subplots. Fantastic. And then finally, we are going to go ahead and add our initial values. So we're going to do fig.add scatter. We're going to say x is going to equal idx, y is going to equal t. We're going to do name, well, first we're going to do mode equals lines. And our name is, of course, going to be at time 0. T equals 0. And yet again, as we do before, we're going to create the rest of our plot through a for loop. So let's go ahead and get started with that. All right, in our loop, we're going to say for n in range 10,000. Because as we set up above here, we're going to have this for 10,000 time steps. So that is our 10,000 time steps. We're going to say b is going to equal 1 plus 2 times r times our t going from 1 to -1. And then to this, we are going to, add r times t from -2 to 0. And then finally, we're going to add r times t going from 2 onwards. And that creates the second part of our equation there, that bottom of the division, or the other side of the equilibrium that we're going to use to solve our linear algebra array that we've got. But moving on from here, we need to set our initial points. So we're going to say that our b initial at our first endpoint is going to plus equals r times r t at 0. And then our last b, -1, is going to plus equals r times t at -1. And then finally, we can do our linear solve. So let's go ahead and get on with that. All right, to do that, we are going to say that t from 1 all the way to -1, our full range of values, is going to equal scipy dot linalg dot solve banded. Say 1, 1. I think the AI got it right. From A, B to B. And finally, we need to put our if loop in so that we can kick out each of our little plots that we're going to have. So we're going to say that if n percent 20 0, we're going to do fig dot add scatter, x equals idx, y equals t, mode equals lines, And our name is going to equal function of t equals squiggly lines n minus 1. I think that should be all good. So now we can go ahead and show our figure. Realized I had an addition here. Let's try that one more time. Hold on. All right. I've also got little lowercase t here. That should be uppercase for our temperature, not our time. Our final error here is that we're going from -2 to 0. We should be going from 0 to -2. All right. Fantastic. So as you can see here, we've got a very similar plot to what we had before, where you can see as we move through time, we're moving from a very stark difference where at the very end it's 50 and 80 to gradually coming up to like a perfect straight line between the temperature gradient between the initial point and the start point, or the end point, going from 50 degrees C to 80 degrees C. So now we can move on to the next portion and see one of the issues with the Crank-Nicholson differencing. All right, let's recreate our figure here. So now we are going to show how these become unstable. And what we are going to do is we're going to change our time step from 1 second to 10 seconds. We're going to run all. And as you can see here, because we're using the Crank-Nicholson, in the beginning, we are not getting the accuracy that we want. But as you can see, in the middle throughout, we are still correct here. We're still getting to the point where we're starting at very little, like big drops between the start and the end point, and we're making it to a point where it's almost a straight line between our 50 to 80 degrees, despite a little bit of inaccuracy at the beginning. So we can see how the Crank-Nicholson allows us to use any value of R, but does result in some inaccuracy at early times at large time steps. So I believe that is the end of homework 2 for process dynamics and controls.